In this video, we're going to learn about conservation of momentum. You guys recently looked at a PhET simulation, and in that simulation, you should have noted for both 1D and 2D scenarios, the total momentum of those objects before and after collision doesn't change. And so in that document, you should have found the conclusion that the total momentum initial, so this is before collision, equals the total momentum after collision. And this is true for any number of objects that are colliding. This is also true for objects that are exploding. So, for example, if you start out with one object and it explodes into several objects, conservation of momentum also applies. And I just want to talk about where this comes from here, and then we will look at some examples. So let me just first expand this a little bit. So when we say total momentum initial equals total momentum final, the momentum initial is the sum of the mass of each object, so we'll say mass of I, times that object's velocity, v of I, and that is equal to the sum of all of the masses after collision, so m final, times their velocity, v final. And here, whether the direction is to the left or to the right, plus or minus, really matters. So make sure you're including those negatives and positive values. Initial means before collision or before explosion, and final means after collision or after explosion. In the lab, you also learned about the two categories for collisions. We have elastic collisions and we have inelastic collisions. For both of these collisions, the total momentum is conserved, but for elastic collisions, the total kinetic energy is also conserved. And we haven't talked about energy yet, but we learned in the lab that the total kinetic energy is equal to half of the mass of the object times velocity squared. So that total value of all the objects involved in the collision is conserved. And for inelastic collisions, the total kinetic energy decreases. For elastic collisions, the objects tend to bounce off of each other, and for inelastic collisions, the objects tend to stick to each other. So I wanted to show you another way to get to this conservation of momentum idea other than the PhET lab that we looked at. And we're going to start by looking at Newton's third law. So what Newton's third law tells us is, let's just say we're dealing with two objects for now. So we have object 1 and we have object 2, and they're going to collide, and when they collide, they apply a force to each other. And what we know about this force is they are equal. So what we can say is the force that object 2 acts on object 1, that's going to be equal to, in opposite direction, of the force of 1 on 2. So one way to write Newton's third law is F1 on 2 is equal to the negative of the force of object 2 on 1. So we're going to start here, and we're going to actually be able to get to that law of conservation of momentum. So what we can do here is we can multiply both of these by the time that those objects are in contact for, right? Because when they collide, they're in contact with each other for the same amount of time. And we know what this quantity is here, force times time. This is equal to impulse. And so what we could say here is the impulse of object 1 acting on 2 is the negative of the impulse of object 2 acting on object 1. And remember, impulse is equal to change in momentum. Change in momentum is equal to the momentum final minus momentum initial. And so what we can do here for each of these is we can replace that impulse with change in momentum. So this right here is the change in momentum for object 2. and this right here is the change in momentum for object 1, so negative delta P for object 1. What we're going to do for each of these quantities is write out P final minus P initial. So here we're going to have the momentum for object 2 final minus the momentum for object 2 initial, and this is equal to the negative of the momentum for object 1 final minus the momentum for object 1 initial. And then what we're going to do is get all of the final values to one side, and we will get all of the initial values to the other. And so we're going to distribute this negative. And so if we do that, we're going to have P2 final plus P1 final is equal to P2 initial plus P1 initial. And so here we have the total momentum after collision. So this is P final, and this would be the total, is equal to, and this is the total momentum before collision, P initial. So that's where the law of conservation of momentum comes from. And I always start out problems by writing this statement out here: final momentum equals initial momentum. And then the next step is to write out the total momentum. So we write out this part here. And then what you would do from here, depending on what value you are trying to find, is you could write this out as the mass of object 2 times the velocity of object 2 final plus mass of object 1 v1 final, and that is equal to the mass of object 2 v2 initial plus mass of object 1 v1 initial. And so if you write out this complete statement here, then you're easily able to solve for any unknown value. So next we'll look at some examples of applying conservation of momentum. So this first example is number 28 in the night problems that we have posted on Canvas. And we have a tennis player swings her 1,000 gram racket. So let's go ahead and write down mass, and we'll use mass R for mass of the racket. And that is 1,000 grams, or that's just 1 kilogram. And the player swings the racket with a speed of 10 meters per second. So that would be the initial speed. So let me go ahead and draw a picture of what's going on, and that'll help us when defining these variables. So initially we have this racket, and so here's our racket moving, let's say, to the right. And so this will be V initial of the racket. She hits a 60 gram tennis ball that was approaching her at a speed of 20 meters per second. So we have a ball, tennis ball, and we know the velocity of that tennis ball. So we'll call that V initial and then B for ball. And the ball rebounds at 40 meters per second. So this is the before collision. I like to draw two pictures, one before the objects collide, and then we'll draw another picture after the objects collide. And we already know what the speed of the ball is after it hits the racket. So we'll draw the ball moving, and it says it rebounds, so it must be moving in this direction, and we'll call that V final of the ball. And we do know the mass of the ball is equal to 60 grams, which is 0.06 kilogram. And we know these velocities, so let's just say to the right is the positive direction. So the velocity initial of the racket is equal to 10 meters per second. And initially the ball is moving to the left, so the velocity of the ball is going to be a negative value. So it'll be negative 20 meters per second. And then the velocity final for the ball is given, and that is 40 meters per second. So the first thing we want to figure out is how fast is her racket moving immediately after impact. You can ignore the interaction of the racket with her hand for the brief duration of the collision. So when the ball hits the racket is going to have a force applied to it on the left, And so we want to know what its velocity is. So V final of the racket. Now that arrow to the left, I don't want that to confuse you. That doesn't mean the racket necessarily goes to the left. It might. It'll all come out in the wash when we do the math here. But we do know there's a force to the left on the racket. That doesn't necessarily mean that its final velocity is to the left. So I'm just going to get rid of that so that doesn't confuse you. We actually don't know the direction. It'll come out in the math when we finish doing the calculation. Okay, so anytime you see a collision problem, you should think conservation of momentum. And so here's how you're going to set up that every single collision or explosion problem. Conservation of momentum tells us that the total momentum initial, so total momentum before collision, is equal to the total momentum final. Or you could say the sum of all of the momentums is equal to the sum of all of the momentums, however you like there. And then from here, we're going to write out all of the momentum before collision. So that's going to be momentum of the racket. So momentum initial racket plus whatever the momentum initial of the ball is. And then the final momentum is going to be equal to the final momentum of the racket plus the final momentum of the ball. And then we're given mass and velocity, and we're trying to find a velocity. So we can write out momentum. We're going to use here, momentum is mass times velocity. So for each of these, we can write out m times v. So momentum initial of the racket, that's going to be mass of the racket, the mass doesn't change, times velocity initial racket, plus mass of the ball, velocity initial ball. And then we're going to set that equal to mass of the racket, v final of the racket, plus mass of the ball, v final of the ball. So there's the full conservation of momentum. And all we have to do from here is just solve for the thing that we want, solve for the value that we want. And part A is asking for the final of the racket. So from here, you could plug all of these numbers in, and it looks more like a math problem that you're used to, but I like to solve for the value that I'm trying to find and then plug numbers in last. So I'm going to get V final of the racket by itself. First thing to do that is we're going to subtract the mass, so the momentum final for the ball, so mass of ball, V final ball from both sides. And if we do that, then we're going to have this term alone, so we'll write that here, mass of the racket, V final racket, is equal to, and then we have mass of the racket, V initial racket, plus mass of the ball, V initial ball, minus mass of the ball, V final ball. And then last thing to do here is just divide both sides by mass of the racket. So that's what we're left with on the right side. A very common mistake I see all the time is students will cancel this out with that and just get rid of the mass of the racket, and you can't do that. In order for you to do that, you would have to have this term connected to each of these so that you could factor it out, but that's not the case here. So don't make that mistake. And so now we can just plug numbers in to get V final for the racket. So there's all of our numbers plugged in, and don't forget that the initial velocity for the ball is a negative value, so don't forget to plug that in for velocity initial of the ball. And then we'll just put this into our calculator all at once. And if you plug all of that into your calculator, you end up with a velocity of 6.4 meter per second. So the racket continues moving to the right, which you would kind of expect, right? If you hit a tennis ball, it's not a great enough collision to rebound your hand the other way. In part B, we want to figure out what the average force is that the racket exerts on the ball, given that they're in contact for 10 milliseconds. And we want to figure out, or we want to compare this to the gravitational force on the ball. So for part B, first of all, the gravitational force is just the weight of the ball, and weight is equal to mg, and so that's going to be 0.06 kilogram times that by the acceleration due to gravity, and we'll just use 10 here. So that is equal to 0.6 newtons. So we want to figure out what the average force is acting on the ball and compare it to that value. So we went through this process. We found the velocity of the tennis racket, and they're giving us a time here. And anytime you see time associated with a momentum problem, then what you should be thinking here is the momentum impulse theorem, which says that the impulse is equal to the change in momentum, which is equal to or on average is equal to force times time. The force applied on both objects will be the same. They're in contact for the same time. So it doesn't really matter which object we look at to find the change in momentum, because that should be the same also. And so we'll just solve for the force here. And so force is equal to change in momentum over time. And if we want to do change in momentum, that's going to be, we'll do mass of the ball times the change in velocity for the ball. So that'll be v final ball minus v initial ball. And then divide that by the time. And so now we can just plug numbers in. We're given all of that information. So there's our numbers plugged in. First of all, you have to convert that 10 millisecond to seconds, and 10 milliseconds is 0.01 second. And don't forget that the initial velocity is negative, so you have to include that negative there. And so now we can just plug numbers into the calculator. And we end up with a force of 360 newtons. And this is greater than the force due to gravity, or the weight of the object, which we found to be 0.6 newtons. You could also say that this force is equal to, in order to go from 0.6 newtons to 360 newtons, you would have to multiply 600 by 0.6. So this force is 600 times its weight. We're going to look at 17 from the same document. And in this problem, we have a 300-gram bird flying along at 6 meters per second, sees a 10-gram insect heading straight toward it with a speed of 30 meters per second. And the bird opens its mouth wide, enjoys a nice lunch. And we want to know what is the bird's speed immediately after swallowing the insect. So this is an inelastic collision problem. And this is a problem where when the two objects collide, you can treat them as one object. And so I'll show you what I mean here when we draw the picture. So let's, just like before, I like to draw a before picture. That kind of helps. So we have a bird and it's flying, let's just say it's flying to the right, and we'll make to the right the positive direction. So this will be our bird, and he is flying with a velocity v initial b for bird to the right, and then we have an insect heading straight towards it, moving to the left, and his velocity is v initial s, and that is our before collision. And then after collision, we know that the bird swallows the insect, so you could just treat them as one object moving in some direction. We'll say to the right, most likely to the right, right? In this collision, the bird is way larger than the insect, so the system should keep moving to the right as long as the insect wasn't going too fast. So we'll call this V total. And so let's go ahead and write down some of these knowns here. So we know the mass of the bird is 0.3 kilogram. The mass of the insect, I don't know why I called this S, but we'll just stick with that. The mass of the insect, we called it MS, is equal to 0.01 kilogram. And we need their total mass for the after collision, so we'll call this mass total is equal to 0.31 kilogram. And what else do we know? We know the velocity for the bird, the initial bird, is equal to 6 meters per second, and the velocity for the insect, the initial s, is equal to well, it would be 30, but since the insect is moving to the left, we'll say negative 30 meters per second. Okay, so we have all of our knowns written down, and so let's go ahead and start by writing down conservation of momentum, and that says that the total momentum before collision is equal to the total momentum after collision. The total momentum before the collision is going to be the momentum of the bird initial plus the momentum of the insect initial, and that is going to equal the total momentum of both the bird and the insect after collision. So we'll call that P total. So momentum of the bird initial, that's going to be mass of the bird, V initial bird, plus mass of the insect, V initial insect, and then that is going to equal the total mass times the total or the final velocity. We'll call that V final. And we want to figure out what that final velocity is. So let's go ahead and solve for it by dividing everything by the total mass here. And if we do that, then we have momentum of the bird plus momentum of the insect, all divided by the total mass. And so now we'll go ahead and plug our numbers in. So there's all of our numbers plugged in, and don't forget that the velocity for the insect before collision is negative, so you got to include that negative 30 meters per second. And so now we'll just plug our numbers into a calculator and get our final velocity. And we get a final velocity of 0.48 meters per second. So next we're going to look at an explosion problem. This is number 20. And here we have a 50 kilogram archer standing on frictionless ice, shoots a 100-gram arrow at a speed of 100 meters per second. And we want to know what the recoil speed of the archer is. So let's go ahead and draw a picture to show what's going on here. So here's a picture of what's going on. So before we have the person and the arrow system, and everything is at rest, and then the person is going to release the arrow will move to the right, and the person is going to recoil the other way, and we want to figure out how fast that recoil speed is. So no matter what, if you ever shoot an arrow or a rifle or something like that, you're always going to feel a recoil when you do that. Now here they say that the ground is ice, and what we're assuming here is that no momentum will be lost to the ground. So if you think about shooting a rifle, you don't slide backwards, right? Your hand might recoil, but since there's friction between you and the ground, you're actually not going to slide on the ground. So conservation of momentum is still applied in that scenario, but the momentum was converted, or the momentum was transferred to the earth, and the earth is so massive that that's not really going to affect it. So here we're saying that this is ice. That way we can figure out what the person's recoil speed will be when he launches the arrow. Let's go ahead and write down some of these values here. So first of all, this is like the opposite of a collision, right? We're starting out with everything together, and so we can say that this is the total mass, and the initial velocity of the system is 0. And then after the arrow is released, then the person, we'll call this V of the person, is going to be the value that we want to figure out. And then we have velocity of the arrow, which is moving to the right at a given velocity. So we have the mass of the arrow and mass of the person. So let's go ahead and write out these values here. Mass of the arrow is equal to 100 grams, which is 0.1 kilogram. Mass of the person is equal to 50 kilogram. And then we have the total mass is going to be 50.1 kilogram. we have the velocity for the arrow is going to be equal to 100 meter per second. And we want to figure out what the recoil speed of the archer is, so that's v person. And so we're going to set up conservation of momentum just like before. So the total momentum before collision, or in this case before explosion, is equal to the total momentum after explosion. The total momentum before the explosion is mass total times the velocity of the system, which is equal to 0, right? So the total initial momentum is 0, and that is equal to the momentum of the person plus the momentum of the arrow. So here we have 0 equals momentum of the person is the mass of the person times velocity of the person plus mass of arrow, velocity of arrow. And so now we just need to solve for velocity of the person. And so we're going to get mass of the person, velocity of person equals negative mass of arrow, velocity of arrow. And then finally, velocity of person is negative mass of arrow, velocity of arrow over mass of person. And so now we can just plug those values in here. And if we plug that in, then we get a value of negative 0.2 meter per second.